This is Unit 2, Lesson 4, Differentiability and Continuity, Part 1. This lesson is about connecting the two concepts, differentiability and continuity. So, the biggest question to ask yourself is, if you know a function is continuous, does that mean that the derivative exists at a specific point on the entire curve? Or if you know a function is differentiable at a point or on the entire curve, does that mean it's continuous? So let's talk about that to begin with. So one thing that we talked about in the last lesson was the local linearity of a point, at a point. A function that is differentiable at a point also has local linearity at that point. So this is telling us in order for a function to be differentiable at a point, the graph must be continuous and smooth at that point. When we say a function is differentiable, that means the derivative exists and we can take the derivative. That's what it means to be differentiable. So we have this formal definition of what differentiability at a point means. It means whenever you have a function f of x and we say it's differentiable at x equals c, what we're saying is this is true if and only if the limit from the left equals a real value and the limit from the right equal that same real value. So that means that the limit is finite and we can take the limit from both sides. Okay, how might this fail? How can f prime of a fail to exist? So we've seen examples of that already. Things like a corner or a cusp or a vertical tangent line or a discontinuity all cause the derivative to not exist. So here's our first example. Okay, example 1 is given the graph of f of x equals the absolute value of x minus 1, what is f prime of x as x approaches 1 from the left? So that means we're approaching this curve from this side of 1, and it's going to follow the curve because that part of the curve is linear, so the derivative, the slope, or the tangent line is going to have this exact same direction. So I'm going down 1 and over 1, so I get negative 1. But as I approach from the right-hand side, as I draw that tangent line from the right-hand side, what I see is now I'm going up 1 over 1, so I have positive 1. So is the function continuous at 1? And the answer to that is yes, absolutely. The limit from the left and the limit from the right will equal each other, and they will also equal the value at f of 1. But is it differentiable at 1? And the answer to that is definitely no, because we see that if we take the limit as x approaches 1 from the left of f of x, f prime of x, that is not going to be equal to the limit of the derivative as we approach from the right of f of x. So there is no derivative. Okay, so next example. So now we have the cube root function, and we're supposed to use the alternate form of the derivative, the limit as x approaches c of f of x minus f of c over x minus c, to show that the function has a vertical tangent line at 0. So that's where we're going to do our limit definition. So we're going to take the limit as x approaches 0 of the cube root of x minus the cube root of 0 and this is all going to be over x minus 0. So this is going to give me the limit as x approaches 0 of the cube root of x over x when I simplify everything. So if I simplify this fraction, I'm going to get the limit as x approaches 0 of 1 over x to the 2/3. because this is actually x to the 1/3 divided by x to the 3/3. So when I subtract those, I get a negative 2/3. So if I write it this way, and what you can see is this is going to lead us to 1/0. So the limit is undefined. And we look at the graph, what we see is at 0, oops, that's not 0. What we see at 0 is that we have a vertical tangent line Now we can see that this is definitely a continuous function. Every limit exists, every value exists, and they're equal to each other, but at that one point, it's not differentiable. Okay, so next example. Now we have the graph of f of x equals 1/x plus 2 squared. So it looks like that picture there. So we're supposed to describe the derivative of f as x approaches -2 from the left and from the right. So we don't have to be super formal because we're just describing. So we can say as x approaches 2 from the left, f of x is approaching infinity, and as x approaches 2 from the right, f of x is approaching infinity, and we can see that from the left and from the right. So given the derivative is this function, f prime of x equals -2/x plus 2 to the third, use the formula to evaluate the derivative when x equals -2. So we're going to do f prime of -2. We're going to substitute that in, so we get -2 over -2 plus 2 cubed. So we're going to get -2 over 0, which is undefined, which is exactly what we would expect from what we mentioned right here. Remember that not only do they have to equal each other from the left and right, those limits, but they have to have a finite value. So it's not enough that they're the same from the left and right, they also have to equal a finite value. Okay, so now how is this related to continuity? So differentiability implies continuity. So what we can say is if we know for a fact that f is differentiable at a specific point C, then f has to be continuous at C. That is absolutely given. So a function is differentiable at C, then it's continuous at C. So differentiability implies continuity. But the opposite is not true. It is possible for a function to be continuous at C and not be differentiable at C. So continuity does not imply differentiability, because you could still have sharp corners, cusps, vertical tangent lines, or discontinuity. So let's write the contrapositive to the statement. If a function is differentiable at C, then at x equals C, then the function is continuous at x equals C. So we're going to contradict both the hypothesis and the conclusion and switch their order. So we would say if f is not continuous at x equals C, then f of x is not differentiable at x equals C. And that is going to be true. Okay, so example 4. Describe the x values at which the function g of x equals the absolute value of x squared minus 5 is differentiable. Justify your answers. Okay, so when you're looking, we have two corners here. So right here we have a corner, and right there we have a corner. So we have corners. Okay? And so we want to find where that happens. So if you notice, I've covered it up, but let me erase that just a little. It's not happening in the integer values, so we have to find them. So our corners are happening where g of x equals 0. So we need to find those. So what we need to do is we need to take x squared minus 5 equals 0. Solve this for x. So plus or minus the square root of 5. So here is minus the square root of 5 at that point, and the other one is positive square root of 5. Okay, so we are differentiable everywhere to there, skipping that point, clear around the curve till we get to that square root of 5 point again, skip that, and go on. So we would write it this way. G of x is differentiable on negative infinity to negative 5 union, then we have the rounded part here in the middle, negative square root of 5 to positive square root of 5. So we've come around the rounded part, then we have to go beyond that. Union square root of 5 to infinity. And that's how you would describe that. So I'm going to stop here, and in the next video, I'm going to do some more examples.